Alright folks, welcome to today's lesson. We're going to be talking about regression analysis, and I will give you guys some examples using Python in Jupyter Notebook. So let's get started. So what is regression analysis? Imagine you're trying to predict your grade in math. You might notice that your grade depends on how many hours you study, how much sleep you get, and how many assignments you complete. So regression analysis is a math technique that helps find out how much your study time, sleep, and assignment affect your grade, which one has the biggest impact, and how to predict your next grade based on these factors. So what does it do? Regression looks for relationship between things. It's like saying, if I study more, will my grade go up, or does a higher price mean fewer people buy a product? It captures those connections by studying data. So let's take a look at some real life examples. Suppose you are running a lemonade stand. Your sales depend probably on the price of lemonade. Let's say maybe the temperature outside, if it's hot or if it's cold, and the day of the week, maybe if it's weekend or if it's Monday or Tuesday. So regression analysis helps you figure out how much sales go up when it's hot, or how much they drop if you raise your price. Which the two kinds of variables that we have in regression is the response variable, which is also known as the dependent variable. This is what you're trying to predict. An example will be the lemonade sales. And then we also have the predictor variable, which is also referred to as the independent variable. And these are the things that might affect the result. Example will be price, temperature, day of the week. And why does this matter? Regression helps business, data scientists, and students make prediction like sales, grades, or weather, understand what matters most, and make data-driven decision instead of guessing. What is a simple linear regression? So think of it as drawing the best straight line through a set of dots on a graph, as you can see here. And the line helps you predict one thing like your test score using one or other things like hours of study. And for example, if you study more hours, your score usually goes up, and we can use regression to find that pattern and make prediction. So the formula that we're going to use is y equals to beta plus beta 1 x1, and then plus we also have the epsilon, the random error, and this is the tiny difference that happens by chance. And then the y here is what you are trying to predict, example your test score, and then the x here is the factor that might affect it, example if you study hours, and then the beta 0 is the starting point, intercept, it's your score when you studied 0 hours. And then we have the beta 1, the slope, how much your score changes for each extra hour of study. So this equation draws a line that best fits the data point between study time and then the test score. So three kinds of relationship here. We have the positive linear regression or relationship. When things goes up, the other also goes up. Example will be more study hours equals higher score. So as you can see, this is a positive one. So let's say we increase it here, it goes up. And then if we increase, it keeps going up. And if let's say this is 1, 2, and then this is 3. So you can see this will also keep going up. And if this is 4, we keep increasing, it will keep increasing as well. So this is positive linear regression. And then for negative linear relationship, when things goes up, the other goes down. As you can see here from this, when things goes up, it goes down here, right? And then when it keeps going, it keeps going down. So vice versa. These are the relationship between negative linear relationship. And then also we have the no linear relationship. We have no clear connection. Example, the number of pets you own doesn't affect your math score, and that line is a flat line, as you can see from here. This is the line. So why does this matter? Understand how two things are connected, predict outcomes like grade, sales, or speed, and then we can make decision out of this predictions. Now, what is multiple linear regression? We already learned that simple linear regression predicts one thing using one variable. Now, imagine you want to predict some time using many factors at once. That's multiple linear regression. Think of it like this. If you want to predict your final grade, it might depend on how many hours you study, how many hours you sleep, and how many assignments you complete. So each of these factors has a piece of the prediction. So let's break down the formula. This is the formula that we're going to use for multiple linear regression. And then the y here is the thing you want to predict, your final grade. And then the x, x1, x2, all the way to, let's say, however, whatever x we have, the factors that might affect it. So that is study hours, sleep hours, assignment, etc. And then we have beta 1, the starting point, your grade if all of the other factors were 0. And then we have the beta 1, beta 2, etc. So the weight or importance of each factor, how much each one change the result. And then we also have the epsilon, random error, a small unpredictable difference like being tired or test difficulties. So the model combines all these effects to make one prediction. Predicting from a sample. In real life, we don't know the true value of these betas. So we estimate them using data. For example, by studying a sample of students and their grades, we write the estimated equation like this. So we have the here the hat mean we are predicting not using the real unknown values, as you can see here from this equation. So we also have the residual, the little difference. After making prediction, we will notice that the model isn't perfect. There is a difference between the actual value and then the predicted value. So that difference is called residual. It tells us how far off our prediction was, like guessing your grade will be 85, but you got 88. So the residual will be what? +3. So in summary, multiple regression uses many factors to make better prediction. It helps you figure out which factors mattered most, and the residual shows you how accurate your prediction are. The goal is to make residual as small as possible, meaning your model is accurate. Now, let's take a look at this graph. What is happening in the graph here? Imagine you have a bunch of dots on the graph. As you can see, we have so many different dots on this graph. And for example, x equals to the hours you studied and y equals to your scored on the test. Each dot show one student's results. Now we draw a line through these dots that best shows the trend. So as you can see, we have this blue line that we draw that shows the best fit, and then the trend. So how score changes when study changes. This line is the regression line, which is written as y beta equals to b 0 b1 plus x. This is the equation. And then what are the little gaps? Not every dot falls exactly on the line. That is normal. The vertical gap between a real dot and the line is called the residual error, and it is written as e equals to y minus y hat. And then the y actually the actual value, the real score, and then the y hat is the predicted value, the score the line thinks it should be. So the residual tells us how far off the prediction was. And how do we find the best line? We want the line that is close as possible to all the dots. So to do that, we use a clever math trick called the ordinary least square method. And it's like this: measure each residual, each gap, and then square each one to make them positive and give more weight to big mistake and add them all up. So choose the line that makes this total small as possible, and then the total is called the sum of the square errors. And then the smaller the sum of the square errors, the better the line fit your data is. So think of it like you are trying to draw a line through a scatter point with your pencil. Every time your line is far from the dots, you get penalty points. So the best line is the one that gives you the fewest penalty point overall. So let's talk about regression model treat all predictor variable as numerical. So first, what are predictor variable? Predictor variable are the inputs, the things that might affect what we are predicting. For example, if we are predicting sales, our predictor value might be price, advertising, budget, season, if it is summer or if it's winter. And then the regression needs numbers. Regression only works with numbers, but some variable like season, gender, color are categories, not numbers. So we can't just plug in summer or winter as test, right? That's where dummy variables comes in. So what is a dummy variable? A dummy variable is a simple way to turn words into numbers. For example, if we are selling high season, we can write D equals to 1. If we are selling in off season, we can write D equals to 0. And then this lets computer understand the categories as numbers. So the reference or the benchmark category, when we have two categories, say high season and off season, one of them becomes the reference category. And then in our example, D equals to 0 equals to off season becomes to the reference. And then we have D equals to 1 equals to the high season. So the regression model will compare high season to off season to see how much the season affects sales. So in short, regression only works with numbers. Dummy variables turn categories into numbers, zeros, ones, and ones, and there will zero groups the reference or the benchmark, and the model compares other categories to this reference. Now let's take a look at this example, and let's jump into Jupyter Notebooks, and then we will solve it there. All right, let's take a look at this example. A student wants what college factors influence post-college earnings. To answer this question, the student gathered information from 116 colleges on annual post-college earnings, average annual course graduation rate, percentage of student paying down debt, the location of the college. Using this data, estimate the linear regression model. So we have the formula N equals to B beta B1 cost, B2 grad, and beta 3 debt, and then beta 4 CD plus the epsilon, which is our error. So predict the annual post-college earnings if a college average annual cost is 25,000, and if its graduation rate is 60%, and its percentage of student paying down debt is 80%, and it's in CD. So to be able to do this, first we import the college data into Pandas data frames and label it's my data. So import Pandas as PD, and then my data equals PD read Excel regression. This is our Excel file, and then the sheet that we want in the Excel file is college. And then if you run my data.head, it will give us our first 5 data, and then we can visualize the data here. So the next step here is to use the OLs and fit function statements to create linear model, which we label multiply. Note that we use the plus sign to add predictor variable, even if we believe that the negative relationship may exist between the response variable and the predictor variable. You will not see it output after your implementation this step. So let's start. So we first import our start model, and then if we first import our start model .formula.api as smf, and then multiply equals to smf.ols, and this smf.olsl tells Python I want to build regression model using the ordinary least square method, and inside it you define the formula earnings is approximately equals to cost plus grad plus debt equals to the location, and any is what we want to predict, the response variable, and then the cost, grad, and debt and location are the inputs, the predictor variable. So the plus sign don't mean addition, they mean includes these variables, and then my data equals to my data tells it where to find a column from the data frame you loaded. And then step 2, the dot fit does the functional calculate the regression line that best fits your data. It's like saying, okay, now that I know what to predict, what data to use, figure out the best equation. So after this line runs multiple, now stores your entire regression model, which includes the intercept, which is the 1000. So now we use the use params property to see the parameters of the model. So as we can see, we have the intercept, we have the location, and then we have the cost, we have the grad, we have the depth, and then the data type is float. And then when we run multiple dot params, and then we put the cost here, we can also see the cost here as well. So this is the cost. And then now we can use the p-values property to see the p-values. But what does the p-value do? So think of p-value like a trust meter for each variable effect. A small p-like value like 0.01 or 0.03 means you can trust the variable. It's very unlikely the pattern happened by accident. A big p-value like 0.4 or 0.7 means the pattern could easily be just random noise. You can't be confident it really affects the outcome. So the magic cutoff is 0.05. In most studies and in most data science machine learning building models, we have the cutoff to be 0.05. That means p-value less than 0.05, strong evidence the variable matters, so we keep it. And if it's greater or equals to 0.05, it's weak or no evidence, the variable matters, so we might drop it. So that is the meaning of the p-value. So that's how we have to calculate for the p-value. And then we also use the summary method to view the summary regression output. And then as you can see, so multiple dot summary, and then we put the open parenthesis, close it, and then it will give us all our R squared, adjusted R squared, F statistics. It will give us all that we need: intercept, the cost, the grad, and then it also gives us the probability skews, k-steers, but we don't need to go into details of all of this. And then note, if you want to use the non-city as the reference, then we can use the following code. So multiply to cost smf.orsl formula, earnings, and then cost plus grad plus depth, and then the location, and then the treatment will be reference equals to non-city. So this is the code that we will use, and then we put fit. And then if you run it, multiple to.summary, this is what you will get as well. And then the next step is to be able to, if we want to create our own dummy variable, we can use the following formula. So my data equals city, and then my data equals location, and then equals to ct.istf type and integer. So then if you run it, my data.head, this is what we get here. And as you can see, the city becomes 100, 100. It gives us a numerical variable that we need. So now, instead of location, we can just use city. So multiple 3 equals to the smf.orsl formula, earnings, cost plus grads plus depth plus city, and data equals my data.fit, and then multiply equals to summary. And then as you can see, we have our regression result. So now we use the predict method to make prediction by supplying relevant predictor values in Pandas data frame. So the prediction that we have, so we know in the question we have cost to be 25,000, and then the graduation rate was 60%, and then the depth was 80%, and the location was city, right? So the multiple.predict uses this regression equation, its len, including your intercept, which we already calculated, to compute the prediction earnings. So behind the scene, earning will be equals to what, and then when you run it, you'll be able to get our earnings, which is 45,408. We can also decide to use this equation, and city, we know our dummy variable for city was 1, and then when you run it, you'll be able to get the same result as this one. So this is how you work on this example. Let me know in the comment section if you have any question. I can jump in to assist you.